Ed Chekmenev is going to tell us about the idea of whether, on other planets, there's also actually some kind of parahydrogen effects going on, and whether they affect the magnetism of Jovian planets. So a very new idea, and I'm extremely excited to hear about it. Thank you very much. Take it away.
Thomas, thank you very much for the introduction. First of all, I'd like to say that I'm really excited about this conference. It's been amazing, and I'm happy to be the concluding presenter. So my lab is now based at Wayne State University. I've transitioned to Wayne State University about 2 years ago. I'm now primarily based in the Department of Chemistry and have in Karmanos Cancer Institute with the idea of moving parahydrogen-induced polarization to biomedical applications. What I've been going to be talking today, though, is going to be quite different from what we typically do in our lab with parahydrogen, SABRE, and other hydropolarized technologies. And today I'm going to talk about Jovian planets, which has been more like, a side project for us. So I'm going to start with a whole lot of background during my presentation today. And the motivation for this work is obviously very much different. Magnetosphere protects planetary life. Magnetospheres dominate the weather patterns on many planets. And space science is a really cool thing to do, at least in my opinion. And rarely in our careers, we get to do anything related to space science. And this project has been, this nice opportunity. So the big question that we are trying to answer is why planets have magnetic fields. So for many planets, it's quite obvious why these planets have magnetic fields, and some planets, such as, for example, Venus and Mars, they don't have magnetic fields. Surprisingly, all the Jovian planets, and here what we mean by Jovian planets, gas giant planets, which follow the name of Jupiter, thus Jovian as the name, all of these planets have no exception. All of them have strong magnetic fields, which is kind of surprising. So I'm gonna start with a little bit of a background just to bring everyone on the same page, and I'm gonna talk about very generic stuff, magnetic field of Earth. So Earth's core is electrically conductive. It consists of 85% iron, 10% nickel. Most importantly, it's a fluidic electrically conductive core. So as our planet rotates around its axis and goes around the sun, Coriolis forces drive the planetary motion inside of our planet, thus generating the dynamo moving inside of our planet, resulting in persistent magnetic fields on planet Earth. So this is the reason why we have this 30 to 50 microtesla magnetic field on planet Earth. So this all has been fantastic, and back in 50s and 60s, some scientists started to realize that other planets, such as, for example, Jupiter, may have magnetic field based on the radio emission. But everything has really changed when Pioneer 10 flyby mission reached Jupiter on November 6, 1973, and indeed confirmed the presence of strong magnetic fields on Jupiter. So as a result of this pioneering discovery, very quickly scientists came up with the dynamo theory for Jupiter. So because there is no substantial presence of metals, but there is a whole lot of hydrogen and a whole lot of very high pressure, a metallic hydrogen can potentially exist at these high pressures. And as a result of that metallic hydrogen, it has been theorized that metallic hydrogen can be this fluidic electrically conductive medium, and as a result, these conductive layers of hydrogen may move, of metallic hydrogen, I should emphasize, and thus resulting in the persistent magnetic fields of these planets. Metallic hydrogen has been predicted back in 1935. Experimental validation of creating metallic hydrogen is still questioned. So here I'm presenting some of the results from this science paper in 2017. And they've been able to pressurize the samples to very high pressure. The experimental validation in this particular case is really down to using iPhone camera to be able to say that these samples are significantly more reflective, and thus they must be made of metallic hydrogen. So assuming that metallic hydrogen is indeed a thing and it exists in these planets, and if we try to analyze the magnetic fields for, and really compare the fields for these planets, and I apologize for the low quality of this picture. If we take a look at the Earth as kind of like as an example for the fields, the magnetic field deviation, or the magnetic field axis deviation from the rotational axis, is only 12 degrees, which is nice because that's what should follow from the dynamo theory. There should be some small deviation from the rotational axis, and this is also the case for Jupiter and also for Saturn. As we see, there are small tilts of the magnetic fields with respect to the rotational axis, and that's great for this theory of metallic hydrogen as a dynamo. There is a problem, however, for Uranus and Neptune. So the big problem here is the axis of the rotation is very much different from the axis of the magnetic field, which is like wildly challenging for this theory. It's minus 59 degrees for Uranus, minus 47 degrees for Neptune. Again, I'm emphasizing that all of these planets have sufficiently high magnetic fields. It's very much comparable to Earth, with the exception of Jupiter. Jupiter is just a mass planet with ginormous magnetic field, 15 times that of Earth. So there are several challenges for the metallic hydrogen theory. And I mean, one thing that we need to kind of remember here is that metallic hydrogen theory was really introduced for Jupiter and Saturn before the flyby missions to Uranus and Neptune. So the problem for the prediction here is, according to the metallic hydrogen theory, the internal pressures of Uranus and Neptune are just too small. There is not supposed to be any metallic hydrogen, according to the metallic hydrogen theory. So if this is really the case, then there has to be something else. And another big problem, I would say, for the metallic hydrogen theory, it was universally introduced way before the parahydrogen induced polarization was demonstrated in the 80s. And here we are, a community of parahydrogen researchers trying to use parahydrogen for the application in magnetic resonance. So our fields are very much decoupled with the astrophysicists. So as a result of these challenges in the context of Uranus and Neptune, a modified dynamo theory for Neptune and Uranus has been proposed. And the things that I would like to emphasize here is all kinds of ionically conductive materials have been proposed to exist in these two planets. There is fluid ice, all kinds of interesting states of methane, ammonia, hydrogen sulfide, potentially existence as layers, even rains of diamonds have been proposed as electrically conductive fluidic layers to be able to sustain this dynamo. So our knowledge, unfortunately, is very poor about the cores of these planets because of the lack of information from the flyby missions, and it's really limited by the AR spectroscopy. The thing that we do know quite a bit is the atmospheric composition of these planets is heavily dominated by hydrogen, way over 80%. And also to some extent by helium. So these are the dominant gases in the atmosphere. So here's something for us should really click. Oh, there is a lot of parahydrogen and it's really cold. Maybe there is some parahydrogen indeed. So my interest in this planetary work was really sparked by the time when we started to collaborate with Voit Gudson, Igor Koptyuk, and Kirill Kovtunov on high field SABRE, and really trying to get into the SABRE field in general back in 2013. And we've been trying to do some really nice work on high field SABRE. So here we're trying to hyperpolarize pyridine, and you see this tiny signal of hyperpolarized pyridine. But what was really striking to me when we analyze the spectra is we see ginormous hyperpolarized orthohydrogen signal. So I really wasn't expecting to see hyperpolarized orthohydrogen signal. And during this nice conference, we actually heard quite a bit about hyperpolarized orthohydrogen. People see that both in SABRE, FIP field, and Konstantin Ivanov did a very brilliant presentation on why hyperpolarized orthohydrogen should exist in our spectrum. So I got really fascinated at that time that, somehow we convert parahydrogen into orthohydrogen and we get this massive polarization. So to me, what polarization really means, and to all of us, it's the degree of alignment with the applied magnetic field. So very quickly, here's the idea. It's quite simple. So the idea goes as follows. Some of these planets, they exhibit very low temperatures of their tropospheres. So in case of Uranus, we're dealing with minus 200 degrees Celsius, which is like, 60, 70 degrees Kelvin. And the idea here is quite simple. In case if we have a rapid exchange or interconversion, I should say, from parahydrogen state, which is singlet, into hyperpolarized orthohydrogen triplet, perhaps we build up such a massive population of hyperpolarized orthohydrogen material, which is really, alignment of the material with the main axis of the planetary field, that perhaps this massive amount can sustain this static magnetic field. So the key prerequisite here is, of course, that this spin relaxation into thermally polarized orthohydrogen must be slow enough with respect to this exchange process. So again, in case if it's fast enough, perhaps it can build up sufficient quantity of hyperpolarized orthohydrogen, and there we go, perhaps we can have this static field. So this is our favorite diagram of orthohydrogen that we all would like to show in our presentations. The reason why I show it here is in case if we use this diagram in order to predict the maximum effect for this theory to happen, it turns out that the maximum is somewhere between 50 and 100 something Kelvin. And this falls very nicely in the temperature range of Uranus and Neptune stratospheres, and to some extent also relevant for Jupiter and Saturn. So, in order for this exchange to happen, we obviously need a catalyst, as we hear during this meeting. We need to accelerate this change, this exchange process. So, on what you see on the left, you see IR image of Uranus. And the interesting part of this image is you see these interesting bands. So what these bands are, these are layers of clouds which are created by tiny microparticles. By tiny microparticles, I mean 1 to 10 micrometer large. What you see on the right is a profile of Uranus troposphere. So if you start very, very high, you get to very high temperatures. So this is like higher levels of stratosphere, I believe. And then as you go down below, the temperature cools down all the way to 60 Kelvin. And then we hit these clouds of microparticles created by ammonia, methane, hydrogen sulfide, and water. So the pressures down below are quite high, and eventually we hit the bottom. And in this case, this is what scientists call the planetary surface, the base of the troposphere. So the key takeaway here is there are lots of these clouds. They're ginormous from the perspective of the planetary scale. These clouds are also at the right temperatures for vast quantities of parahydrogen to potentially exist. So as we also know from some of the work in our field, our catalyst may not necessarily be paramagnetic. In this brilliant paper, Camilla Terenzi and Daniel Kennett have demonstrated that our solvents, our diamagnetic solvents, may cause this relaxation from para to ortho. And that's kind of important here too. Another interesting point that I think you should all be curious right now is our catalyst really active? Do we have any evidence that there is indeed ortho-parahydrogen exchange happening in this particle? So it turned out that this area of research has been very active and very interesting intriguing for many, many years back into 70s and 80s. So if we carefully look through the literature, we find that what happens in some of the planets like Jupiter and Saturn, this stratospheric parahydrogen fraction is very close to the pose phase value. So what this really means in our language, in the language of parahydrogen induced polarization community, the upper levels, the thermally polarized, the high temperature equilibrium, very high temperatures, and also the lower levels of the atmosphere, they're also at very high temperature. So because the interconversion between para and ortho is very slow, so think of this as your broken parahydrogen generator where you don't have efficient catalyst. The entering material that enters your tropospheric level is becoming high temperature material, which is very close to 0.25 fraction. In contrast, in uranium stratosphere, it lies very close to thermodynamic equilibrium. So what this means, whichever part of the uranium troposphere we try to sample, the value of ortho to para ratio is thermodynamically equilibrated to that temperature. So what really this means in our language of having a parahydrogen generator on a planetary scale, we have a lot of catalyst, which is actively equilibrating the ortho-para ratio on these planets, such as Uranus. So this is, to me, was very exciting. When I was reading the literature, I'm like, oh my God, there is a catalyst and it's actually active. It accelerates this interconversion. Again, we don't know if it does it on the time scale, which is relevant to produce high levels of polarization, but that's a theory at this point. Moving on, that's kind of the summary of this theory. We have cold parahydrogen-rich zones of the planets where we have exchange between parahydrogen and hyperpolarized orthohydrogen, which moves back and forth, which is accelerated by aerosol clouds. And in case if this transition is again fast enough, faster than the relaxation processes, we can potentially, well, or the planets can potentially build up these vast quantities of hyperpolarized orthohydrogen. That's the core idea of this theory. So this theory kind of works very well, for example, for Uranus. So again, here you see an image of the magnetic field distribution, or a very, I would say, sketch for the magnetic field distribution. So the key takeaway here is the magnetic field axis is way off center from the planetary core. The magnetic field is not a dipole; it's more like a quadrupole and octupole. The field on average is 23 microtesla, but it ranges from 10 microtesla to 110 microtesla as you go around the planet. And as I mentioned, it has multipolar structure. So the reason why this parahydrogen explanation is good in the context of Uranus is because there is a distribution of the clouds throughout the planet, and this distribution therefore may render different hyperpolarized concentrations all over the place throughout the planet, thus rendering significant gradients in the produced magnetization. So another obvious question that we should be asking ourselves is there enough proton spins in general? So the way our hyperpolarization work, we try to align them along certain axes. So, but in case if there is not enough spins, well, there is nothing really to align. So even if all of them are aligned, the dipole moment is just not going to be significant enough. So the dipole moments for the planets are very well known. Here they are. These are the actual dipole moments in the units of Tesla multiplied by cubic meter. And here is the value of theoretical magnetic moments. So the way these have been calculated, we basically take gamma of protons, their magnetic moment, we multiply and we assume perfect alignment of the spins. So this is like a perfect situation, which we know obviously is not going to happen, but this is our theoretical maximum. And the important factor here is the ratio between known magnetic moment divided by the theoretical moment, and it turns out to be quite small. So what this means, as long as the average polarization, for example, for Jupiter is, let's say, 2%, and even substantially less for Saturn, Uranus, and Neptune, there is enough material to cause this sufficient magnetic moment for the planet. So another obvious question is, can we do something about it? Can we do some experiments in our labs to be able to confirm that these large magnetic fields can be created, or can we actually see some of these fields? So here again, this is very much the work of our entire community, because we've been doing a lot of stuff as a community in the field of hyperpolarization. So this is the work of Stefan Appelt going back to 2005, where they've been studying hyperpolarized xenon gas samples and also hyperpolarized xenon gas in the dissolved phase in toluene at Earth magnetic field. So they've been generating very high levels of polarization in their samples and high magnetization in general. And what they've seen, their samples, the magnetization of their sample becomes large enough to make changes or to make substantial effects on the total magnetic field that their nuclei is seen. And what the way they basically notice that is they see changes in the resonance frequency in their lines. And as hyperpolarized xenon decays, what happens is the magnetization decreases as well. And as a result of that, this frequency shift decreases as well with the decay of polarization, which is nicely seen here. And they've been able to estimate experimentally what this, how large this dipolar field is. And it turned out to be on the order of 1 nanotesla for the hyperpolarized samples. So Stefan kindly did the calculations for the Jovian planets in case of hyperpolarized orthohydrogen and kind of relevant conditions for these planets, and it turned out that these dipolar fields can be as large as 0.2 to 0.3 microtesla at these conditions. So obviously, these dipolar fields are not as large as these planetary fields are. So these planetary fields are substantially higher, but we're kind of getting there. So here I would like to switch to another interesting topic that has been discussed at this meeting quite a lot. This is raser amplification mechanism. And I'm not going to go through the fundamentals or anything of this nature because Stefan Appelt gave a beautiful lecture. The only thing that I'm going to emphasize here is the raser effect is really directly proportional to the gamma squared, which we can do nothing about in case of our proton spins, but it's also proportional to the spin densities and also the polarization values. So this is kind of important because basically as long as we can pump polarization high enough, and in case if we can go crazy with the spin density, perhaps we can create these rasers in our labs. And it turned out to be the case. In fact, raser was a big problem for us as we were trying to study our Parahydrogen-induced polarization samples for biomedical applications at very high concentrations. So the way this experiment works, we bubble the sample in 5 mm NMR tube through a catheter. We remove this catheter, we put the sample inside of the spectrometer, and we open the receiver before we put the sample in. And it turned out that at some point, bam, you have this huge signal coming out. You have no RF pulses whatsoever, and the sample is inserted right here. So another important feature here, we have line narrowing, which has been discussed very well. But the thing that you start to notice is, these resonance frequencies, they're kind of awkward, right? We're dealing with something which happens to be around minus 0.5 ppm. So this is another data set from more recent work of from my lab, from Baptiste and Nwandi, working on diethyl ether, where they're trying to hyperpolarize diethyl ether. And in this particular case, you have superposition of several different spectra. You have thermally polarized, hyperpolarized sample, and the raser spectrum, which is shown here on the right. So what you see dramatic change in the chemical shifts. So obviously we have no other molecules that we're detecting during raser condition because we're not applying any RF pulses, but the change in the frequency is quite dramatic. So again, if we attribute this to the dipolar field creation, here a raser can potentially act as an amplification mechanism and causing these large changes in the chemical shift. So if this is the case, these dipolar fields are now substantially higher than the order of 1 to 4 Tesla through the amplification by raser. So here we have a different sample where we intentionally put a fluorine sensor on it. And here we're hydrogenating in this double bond in the acrylate moiety, and we're producing this beautiful molecule with 2 hyperpolarized proton and our fluorine sensor sitting on the other side. So what we see here is our typical raser, 2 very sharp lines. And again, here you see these are ppm, and we're dealing with very low field conditions. We're doing our experiments at 1.4 Tesla. So the beauty of this spectrometer that we have, and all of us actually have, whoever owns a spin solve, on the proton channel, your fluorine detection comes for free because you're using the same RF coil to be able to detect both of those. So in case if we detect fluorine during raser, so for fluorine to detect, we obviously need to apply RF pulse. As we're producing hyperpolarized material through parahydrogen addition outside of the magnetic, outside of the high magnetic field, and then moving the sample inside of the our 1.4 Tesla machine, there is a spontaneous polarization transfer to these fluorines, and fluorine has this nice anti-phase line, which is the Fourier transform of this stuff. What you see here as a noise is not a real noise. Basically, it's kind of like the overtones coming from 2 megahertz away. So this is a confirmation that during the time when we detect our fluorine signal, there is raser happening on fluorine, on the proton channel, because we're dealing with exact same coil. Our protons are coupling and raser going on the proton frequency. So now what we do in the next experiment, we just pour a lot of substrate. So here we're gonna go crazy. We're gonna increase our concentration to 800 millimolar concentration, most of which is actually getting hydrogenated, and we're getting decent levels of polarization. And if we look at the Fourier transform of this line now, the intensity is now spread over 14 ppm. So the way I explain these lines is we have magnetic field fluctuation during our raser, and the frequency is changing quite a lot. The frequency is changing over 20 microtesla field, so which indicates that during raser condition, our hyperpolarized protons can the dipolar fields created by these hyperpolarized protons can potentially be quite large. It's on the order of 20 microtesla. And of course, one of the criticism here is like, well, maybe you're doing guys something else. Maybe you are saturating your receiver. All of this stuff is feasible, possible. So in order to exclude this from the potential explanation here, we also performed on the detection on the fluorine. So again, RASER is happening on the proton channel. On the proton frequency here, we are opening our fluorine detector and we are trying to sense this hyperpolarized fluorine. So this central line now is breaking out into gazillions of lines, but importantly, we have the same dispersion. We have the 14 ppm dispersion. So this is my favorite slide. We're getting close to the end of the presentation. So it's called, if there would be no COVID-19, our 0.35 Tesla MRI scanner would be installed, and we would be trying to simulate the conditions of this outer, we would be trying to simulate these conditions of Jovian planet, trying to put some ammonia particles in the liquid nitrogen bath, pump it with hydrogen, and see if we can simulate the conditions of these planets and see if we can create the RASER out of them. So in conclusion, a new theory of magnetic fields on Jovian planets is presented. Fast parahydrogen exchange intercurrent conversion explains the magnetic field created on these planets. Large quantities of protons exist in these planets' tropospheres at the right temperatures to sustain parahydrogen-induced planetary magnetism. And parahydrogen-based RASER and other nonlinear phenomena can significantly amplify things that we're seeing, can significantly amplify the dipolar fields, which can also explain this planetary magnetism, even with smaller fraction of protons being hyperpolarized. So with this, I'd like to conclude my presentation, thanking all the people and the funding agencies which were involved, including my collaborators, and you. Thank you for your attention.
Yeah, thank you, Ed, for this fun presentation that really makes us think about other things that we're usually worried about. So there's, of course, as you can imagine, a very large list of questions. So let's kind of start. Do you think that there might be some effects also observable in the mesosphere of the Earth?
I haven't really thought about that. One would really need to look at the temperatures that are happening there, and in case if the temperatures are right, and in case if there is sufficient quantities of hydrogen in general, I think this effect can be actually quite universal. So as Simon Duckett said, parahydrogen is the path to the stars. Well, it could certainly be the path to the planets.
There you go. So here's a question about the mechanism of the polarization that you think might be similar to SABRE. So I guess the question is, in SABRE, for example, polarization is transferred from, say, the parahydrogen onto some other spins, and that's really what allows the orthohydrogen to then be hyperpolarized into a given direction. But it's also really quite likely that, parahydrogen just attaches somewhere and just immediately relaxes away and no polarization gets formed. So in detail, the question is, the couplings in the SABRE always conserve the number of spins up. They only create magnetization because the spins are on different species and the orthohydrogen leaves. What creates a bias to positive or to negative magnetization in Jovian planets?
So this is a very interesting question. And to be honest, the way I would try to answer this question, I would actually try to simulate the conditions and generate this effect in the lab. And that's what we would like to do. And we hope to do it on a very quick notice. But what I actually like about this meeting this week is really the presentation of Konstantin Ivanov, who was really nicely explaining why this effect should be happening in the context of FIP. So as long as your parahydrogen gets attached to something or gets to interact with something that allows to break the symmetry temporarily, that allows for and that potentially can allow for this interconversion and also allow at the same time interconversion into orthostate. So as long as these two things happen, as long as the symmetry is broken temporarily, there is no violation. And again, this was I had the same issue at the beginning. I didn't believe our orthohydrogen in our spectra at the beginning. We were all questioning that quite a lot. But thanks to the community in general, who was able to demonstrate hyperpolarized orthohydrogen in many different samples, I thought this is not supposed to be happening.
Yeah. No, I think this is a very interesting and important point here. So I encourage very much this discussion to go on in the Slack channel. So let me transition to a different topic here, or not topic, but like kind of similar problem, which is that, you know, T1 on orthohydrogen is typically relatively short. So under those conditions on these planets, could it be that maybe T1 of the orthohydrogen is much longer? So that, you know, I guess the problem is, right, if T1 is short and it decays very quickly, then probably not create a very strong effect.
Right. So in case of the relaxation mechanism dominates, in other words, if your relaxation dominates the rates of the exchange, you're not going to see any magic. I don't know the spin physics well enough to be able to say how the magnetization is going to evolve in the absence of the dramatic magnetic field. So here we're dealing with something which is completely new as a field. And I think there's a really huge opportunity for people to contribute and come up with brilliant theories of the dynamics and evolution of magnetization at these very interesting conditions. But I think the fundamental problem is our field of parahydrogen induced and hyperpolarization research has been completely decoupled from the field of the astrophysics and planetary science in general. And we really should be talking between each other as a community, not stay on the completely different ends.
Yes, well, I guess that's maybe good feedback for our next PERM to get more people from planetary science.
Sure.
Okay, good fun. So I guess this is a related question to the previous questions, which is really to do with the direction of the created hyperpolarization, right? For this to really work, the direction has to be determined by a certain mechanism. So what would be the mechanism here that determines this to add into a certain direction?
Right. So this is a really good question. So the question basically goes like, you know, what is the origin of the primordial magnetic field on these planets in case if it actually gets to happen this way? So there are many different ways how the initial field direction may have been inspired. And this may have something to do with either being in the proximity, for example, of Jupiter, which actually has substantial magnetic field. But to me, and there is another part of me which is arguing like, well, on the planet Earth, our magnetic field switches back and forth, right? So we don't know how the field reversals really happen in life. And we also need to realize that these are like giant planets and they get to go through catastrophic events when something massive goes through them. So there is, to me, there's got to be some opportunity throughout the history for the reversals of the field, so for the field to evolve, so to speak. So I'm not really answering the question, I understand, but to me, the origin of the primordial field is probably not important. And there is probably got to be some mechanism why the magnetic field on these planets end up to be in this interesting range of a few microtesla, a few tens of microtesla. So one thing that I'd like to point out here is in these two planets, so Uranus is like significantly smaller, not significantly, somewhat smaller than Neptune, yet it ends up with similar field. And I find that fascinating.
Yeah. Okay, well, there are actually many more exciting questions, such as, you know, are we having a ginormous raser on these planets and other questions. So I very much encourage all these conversations on the Slack channel and